Alright, this is Quiz 5B Part 1. A rocket which has a rest mass of 235,000 kilograms, including 186,000 kilograms of fuel, is sitting at rest in space. When this fuel is burned, it is exhausted from the rocket with a velocity of 38,500 meters per second. For simplicity, we're going to assume that all the fuel has been emitted at once. What will be the final velocity of the rocket? Now I've drawn a diagram of the rocket before. Okay, it has a total mass of 235,000 kilograms. This includes the rocket and the fuel together. Now, because it's considered resting in space, it has no velocity. Now, once an explosion occurs and the fuel has been ejected out of the rocket and propelled the rocket forward into space, we have two separate masses. The mass of the rocket, which is 49,000 kilograms, and then the mass of the fuel, which is 186,000 kilograms. And the velocity of that fuel is 38,500 meters per second. What are we trying to determine? Well, we need the velocity of the rocket. Okay, now in order to determine that, we need to consider a few things for this problem. Okay, so what type of collision is this? Well, it is called an inelastic collision. Okay, what is an inelastic collision? Well, an inelastic collision starts off as one singular mass, and then some type of explosion occurs or some type of collision, and there's two separate masses in the end. Now, with inelastic collisions, the kinetic energy is not conserved, but momentum is. So this is the conservation of momentum. Momentum. Okay, so, but what is momentum? Okay, momentum, we're going to change colors. Okay, momentum is characterized as the letter P, and it is a vector. And it's equal to the mass times the velocity, which is also a vector. Okay? And the conservation of momentum, it must always have the initial momentum, or before, must equal the final momentum, or after. Okay, so let's set up a problem and that proves it. Okay, so we have the total mass, okay, multiplied by the initial velocity, and that is equal to the, let me do this, okay, multiplied by the negative mass of the fuel multiplied by the velocity of the fuel. Now I have this as a negative because the fuel is moving in the opposite direction as the rocket. Okay, so plus the mass of the rocket multiplied by the velocity of the rocket. Okay, so let's figure out what we can cancel out in this problem. And we know that the initial velocity is 0. So this side is just 0. So we have zero equals the negative mass of the fuel multiplied by the velocity of the fuel plus the mass of the rocket multiplied by the velocity of the rocket. Okay, what are we trying to solve for? We're trying to solve for the velocity of the rocket. So let's solve for that symbolically so it's easier to input our givens. So let's just add the mass of the fuel and velocity of the fuel to this side. That equals the mass of the rocket times the velocity of the rocket. And then we just divide by the mass of the rocket to get that its velocity isolated. Okay, so we have our problem. The mass of the rocket is equal to the mass of the fuel multiplied by the velocity of the fuel over the mass of the rocket. Okay, so all we need to do is just plug in our givens and then calculate them, and then we'll have our velocity. So the mass of the fuel is 186,000 kilograms, and that is multiplied by the velocity, which is 38,500 meters per second. And that's all divided by the mass of the rocket, which is 49,000 kilograms. Okay, kilograms cancels out. And we are left with velocity of a rocket, which is 146,142 meters per second. That's it.